The term volatile organic compound (VOC) refers to a broad category of organic chemical compounds that are easily vaporized and that, under typical circumstances, enter the environment or dissolve into water and are present in many everyday items, including paints, adhesives, cleaning supplies, and cosmetics. Once released into the environment, VOCs can travel great distances due to their high volatility, mobility, and strong resistance to deterioration. The aromatic hydrocarbons benzene, toluene, and xylene are the most commonly found VOCs. In humans, VOCs are continuously generated from the human body and are released via breath, blood, skin, urine, and feces.
Moving on, I will be talking about the VOC types that can be taken into the blood. VOC types detected in the blood are not actually specified. It depends on which type of VOC the person is exposed to or it is taken in. Benzene, ethylene glycol, formaldehyde, ethylene chloride, tetrachloroethylene, toluene, xylene, and 1,3-butadiene are typical examples of VOCs that can be present in our daily life. Sources of VOCs can origin from many kinds, such as building materials such as paint, varnishes, caulks, and adhesives. It can also come from home and personal care products such as air fresheners, cleaning products, and cosmetics. Activities such as smoking, dry cleaning, or cooking can also cause VOCs to be taken into the human body. Acute exposures lead to eye, nose, and throat irritation, headaches, nausea, dizziness, and also worsening of asthma symptoms. Chronic exposures, on the other hand, can lead to cancer, liver, and kidney damage as well as the central nervous system.
The concentration of VOC has significantly higher abnormalities of fibrous cell and hemoglobin. For example, benzene after being metabolized in the liver and bone marrow will form into multiple reactive metabolites like benzene oxide, quinones, and also muconic acid. It will then causes cytotoxicity to both hematopoietic progenitor cells and also mature blood cells by depressing the hematopoietic tissue. Not only that, it can also manifest reduced hemoglobin and reduced blood cell count. As hemoglobin is reduced, lesser oxygen will be carried throughout the body. Due to the limited oxygen supply, the muscle cells may not fulfill the normal muscle contractions for daily activities. This reduces the formation of creatinine as VOC is inversely associated with creatinine. In terms of platelet counts, it will be increased by the high concentration of VOC in the blood. This is because the cytotoxicity caused by the VOC will activate the immune system, thus leading to inflammation.
So, taking samples from the disease requires an autopsy warrant and adheres to a set of tiers mentioned, where samples are divided into 3 important tiers. The primary specimens in tier 1 are none other than blood, urine, ocular fluid, and peripheral blood specimens. Blood samples are best obtained from the femoral vein by percutaneous puncture using a 10 ml or 20 ml hypodermic syringe. The leg should not be massaged prior to sampling in order to increase the specimen volume. To obtain femoral samples, some forensic toxicologists advocate clamping the vein prior to sampling. This is so that the vessel is tied and clamped proximally near to the inguinal ligament before sampling. This prevents drawing down of blood from the inferior vena cava and from the inguinal vein. However, clamping the vessel adds time and adds incisions to the autopsy procedure. Once the blood specimens are collected, it is then screened for specific drug classes through immunoassay methods. This can also be known as the presumptive drug test for blood. Cutoffs set by regulatory bodies help classify samples into negative and non-negative, at which the value equal to or greater than the cutoff measurement is deemed non-negative. Confirmatory testing will then be performed on those samples with non-negative results through acquiring an aliquot from the sample, while samples with the screening test resulting negative will not undergo any further testing. The chemical substances that are detected during screening are isolated from the biological matrix liquid for confirmatory testing purposes. This is also known as the detection phase. In cases where it is thought that a person is actively using drugs or alcohol, blood analysis may be necessary. Blood tests are a good indicator of recent substance abuse since the drugs stay in the blood for up to 48 hours. Blood analysis provides a relatively small detection window for drugs because they are quickly metabolized and removed from the body. Depending on the medication and the dosage, drugs in blood can often be detected within minutes to hours as opposed to 1 to several days in urine. Whole blood samples are subjected to blood drug screening tests, employing immunoassay screening followed by reflex to definitive testing.
Solid phase microextraction (SPME) is an innovative and sensitive solvent-free sample preparation technology which provides the analytes that can be examined and identified by the GC-MS easily. SPME can extract the different kind of analytes from the solid, liquid, and gas phase of sample. SPME works based on the principle of absorption and desorption. In absorption, the analyte is absorbed onto the surface of a good silica fiber, and the amount absorbed by the fiber depends on the thickness of the stationary phase coating on the fiber and the distribution constants for the analyte. While in the dissorption process, the needle is placed into the injection port of the analytical instrument, with the fiber is exposed and the desired analytes are dissolved to the instrument. The dissorption time is determined by the time needed to obtain precise extraction for the analyte with the largest distribution constant. Normally, a thick polymer coat is required for absorbing and dissolving volatile compound, while the semi-volatile analytes need a thin coat to maximize the absorption and dissorption. In the investigation of VOC in blood, SPND is used primarily because it develops the analyte capable of GC-MS with the minimum detection limit. Gas chromatography mass spectrometry (GC-MS) is an analytical method that can determine different substances within a test sample most accurately. It is selective and sensitive, offering the most chemicals detection capability. The GC-MS results can be produced in just a few minutes, expediting decision making at the point of sample collection. Normally, SPNE is performed before conducting GC-MS to prepare the analyte capable of GC-MS within the minimum detection limit from the sample. In GC-MS, GC works to separate analyte into individual substances based on its boiling point and polarity by heating and carrying the separate substance that emerge from the GC column opening into MS. Once the substance leaves the GC column, MS ionizes and fragments them using electron or chemical ionization source. Then, the ionized and fragment substance are accelerated to the mass analyzers and separated based on their different mass to charge ratio. MS detector will determine the mass of the substance and identify them by comparing them with the reference in the database. Due to the high volatility of VOC, GC-MS is applied widely in identification of VOC in blood. GC-MS can characterize the VOC specifically with its high resolution, low detection limit, accuracy, and short analytic time.
In conclusion, any organic chemical compounds that have the ability to evaporate under typical atmospheric circumstances are regarded as VOCs. Reducing the concentration of VOCs indoors and outdoors is an important health and environmental goal. However, it is important to understand that there are VOCs of concern indoors and outdoors that do not impact photochemical oxidation and therefore are not regulated by the respective laws. When promoting or utilizing techniques to enhance indoor air quality, it is crucial to make and comprehend this distinction.